All right. I think we're on iterators now. Iterators. Let's see. I already have the book open. Let me expand that. And we're starting off with processing a series of items with iterators. The iterator pattern allows you to perform some task on a sequence of items in turn. An iterator is responsible for the logic of iterating over each item and determining when the sequence has finished. I see. Alright, so for the first sentence, I tell you what an iterator pattern is. Iterator pattern is, let's say you have a list of items, right? You got 1, 2, 3, 4, 5. And you want to act on each one of these in turn. Then you use an iterator pattern, which would be like the first one, act on it. Now look at the second one, act on it. Look at the third one, act on it. Continuing to finish or complete this entire collection that you have. So the second sentence, an iterator is responsible for the logic of iterating over each item and determining when the sequence has finished. So the first thing we described was iterator pattern, just going over and acting on each one in turn, each item in turn in this collection. An iterator is responsible for the logic of giving you the next item that you're going to iterate on, or are going to act on, and determining when you have reached the end of this collection. Okay? Understood? The next sentence is, when you use iterators, you don't have to re-implement that logic yourself. Seems pretty self-explanatory. They haven't explained it yet, but that's good to know. In Rust, iterators are lazy, meaning they have no effect until you call methods that consume the iterator to use it up. For example, the code in listing 13-13 creates an iterator over the items in vector 1 by calling the iter method defined on vect. This code by itself doesn't do anything useful. Alright, and we have some code here, so let me scroll down to it. Move that over. Pull out my editor. I guess I can leave the print there. And we're saying let v1 equal vect, creating a vector. Give it 1, 2, 3. And then say let v1 underscore iter equal v1 dot not insert not enter iter, and then it tried to give me expanded the syntax new v1 dot iter, and it has nothing there, and this doesn't do anything. And what does this warning tell me? Specify type explicitly. Don't know exactly what that means, but let's see if we can run this. Cargo run. And yeah, it ran. We have an unused iterator. Cool. Alright, so what this is trying to illustrate, or what this is illustrating, is that we created an iterator, right? And that is here. We can see the type iter, I32. However, because we haven't acted on it or tried to consume the items within this iterator, nothing has happened. It is lazy. Until we try to do something with it, nothing is going to happen. Continuing onward. Once we've created an iterator, we can use it in a variety of ways. In listing 3-5, in chapter 3, we use iterators with for loops to execute some code on each item, although we gloss over what the call to iter did until now. The example in listing 13-14 separates the creation of the iterator from the use of the iterator in the for loop. The iterator is stored in the v1 underscore iter variable, and no iteration takes place at that time. When the for loop is called using the iterator in v1 underscore iter, each item in the iterator is used in one iteration of the loop, which prints out each value. Alright, so they're just explaining what this below code is doing. So we have the first line, we created the vector. Second line, we create the iterator. and this third section when we create a for loop to go over the iterator. Do one for loop over each item in the vector, in this collection, the iterator. So let's write that out. For value in v1 iter, and we're going to print got comma val, and see what that gives us. Should give us 1, 2, 3. Just close out of this. Got 1, got 2, got 3. Okay, that makes sense. So this is the first item that got consumed and used. Second item in the iterator, or in this list that's being iterated over. And the third item right there. In languages that don't have iterators provided by their standard libraries, you would likely write this same functionality by starting a variable at index 0, using that variable to index into the vector to get a value, and incrementing the variable value in a loop until it reaches the total number of items in the vector. That is a mouthful, but more or less what they're saying is some of the canonical versions of a for loop, where you have for, you initialize your index variable at 0, and then while the index variable is less than the length of your list or array, keep incrementing that up. So you go from 0, 1, 2, 3, all the way to the amount of items you have in your array. And then you use that counter to index into that array and get that variable back. So it'll be index starting at 0, then array index 0, bring that variable out, then go through the loop again, index 1, index 2, index 3. Most languages don't have that anymore. Most languages have iterators. So this is probably not something you would see all that often anymore. But it's good that they noted it. Moving onward. Iterators handle all that logic for you, cutting down on repetitive code you could potentially mess up. Iterators give you more flexibility to use the same logic with many different kinds of sequences, not just data structures you can index into, like vectors. Let's examine how iterators do that. Okay, so what they're saying here is that, one, this style of iterator is less code than the previous thing that they mentioned in this paragraph. And because there's less code, there's less room for us to mess things up. However, another pro for using this iterator pattern is that we can use it on things that are not vectors. We can use it on things that we cannot easily index into, with like the counter thing that they mentioned here. And they're going over that example next. And they're seemingly using the next method. So, the iterator trait and the next method. All iterators implement a trait named iterator that is defined in the standard library. The definition of the trait looks like this. Here's the definition. We have public trait iterator. They have a type item, and then they have a function next. And this next function is immutable reference to self, and it returns an option that is either the item or I guess nothing. Yeah, that makes sense. Keep that there. Notice this definition uses some new syntax, type item and self item, which are defining an associated type with this trait. We'll talk about associated types in depth in chapter 19. Again with the future chapters. Okay. For now, all you need to know is that this code says implementing the iterator trait requires that you also define an item type. And this item type is used in the return type of the next method. In other words, the item type will be the type return from the iterator. Alright, so they're going to go over this in detail in chapter 19, but what they're telling us is this new syntax, type item, and self item, are just references to what the iterator is going to return. So in this scenario, I mean, since it's very generic vector, it might just be t, and they might just have that here somewhere. But if you're going to write this explicitly for I32, then your item type could be an I32, and you can just return I32s, seemingly. The iterator trait only requires implementors to define one method, the next method, which returns one item of the iterator at a time, wrapped in sum, and when iteration is over, returns none. We can call the next method on iterators directly. Listing 13-15 demonstrates what values are returned from repeated calls to next on the iterator created from the vector. So here is the demonstration, and they put in test, so we could write this as well. Create a test function, call it iterator demonstration. And we have let v1 equal vect 1, 2, 3. Let mutable v1 iter equal v1 dot iter. And now we're going to call next on it directly to see what happens. Okay. So we can do assert equals, do this a couple times, v1 iter dot next, and then we're asserting that is equal to sum, and we have a pointer reference to 1, which I guess 1 is on the stack, so it should be copied, but they still put a pointer reference to 1. Okay, I'm not exactly sure about that, but we know what it means. So write this a couple more times. Dot next sum to search. Next sum 3 one more time to show the none case. None. Alright, so what we're trying to see in this, hopefully it works, is that we have I can go over here. We have a vector with 3 items. Make it into an iterator. We call next on it 4 times. So in the first time we see 1, second time we see 2, third time we see 3, and given that it is now empty, the next time we call next, we should get none. And let's see. That seemingly worked. That's supposed to call go. Yeah, there we go. Test. And the test, 1 ran, and it said, okay, it passed. Okay. Moving onward. Note that we needed to make v1 underscore iter mutable. Calling the next method on an iterator changes internal state that the iterator uses to keep track of where it is in the sequence. In other words, this code consumes or uses up the iterator. Each call to next eats up an item from the iterator. We didn't need to make v1 underscore iter mutable when we used a for loop because the for loop took ownership of v1 underscore iter and made it mutable behind the scenes. I see. So what they're saying here is when we're in this example, when we're calling next directly on the iterator, we had to make it mutable. And the reason why we had to make it mutable is because Each time we call next, we're changing the state of the iterator. Given that we're changing its state, we're mutating it. Okay, that makes sense. So then they brought up, well, above here, when we used the for loop, we didn't have to make it mutable. What's up with that? So what they said to counter that is the for loop itself took ownership of v1 underscore iter and made it mutable behind the scenes. So yeah, the difference between this and this is explicit, and this implicitly behind the scenes made v1 underscore iter mutable. Okay. Also note that the values we got from the calls to next are immutable. Also note that the values we got from the calls to next are immutable references to the values in the vector. And that is the part that didn't make sense to me earlier, but now it does make sense. This is a reference to 1 because this is immutable. That's what they just explained. Even though the iterator itself is mutable, the values that we're getting back when we're calling next are immutable. And thus we have the reference 1, reference 2, the pointers. The iter method produces an iterator over immutable references. If we want to create an iterator that takes ownership of v1 and returns own values, we can call into iter instead of iter. Similarly, if we want to iterate over mutable references, we can call iter mute instead of iter. Okay, so here they're listing out the different methods we can call for different purposes. Iter, the one we called earlier, returns immutable references. Into iter returns owned references. Like you take ownership over the item that was in the vector that you are now consuming because it was in the iterator. And then similarly, we have iter mutable, which instead gives you a mutable reference to that item that was in the iterable. Methods that consume the iterator. The iterator trait has a number of different methods with default implementation provided by the standard library. You can find out about these methods by looking in the standard library API documentation for the iterator trait. Some of these methods call the next method in their definition, which is why you're required to implement the next method when implementing the iterator trait. So what they're saying here is the iterator has a number of different default methods or methods with default implementations given by the standard library. So there are methods for the iterator that you don't have to write yourself, they just provide it to you. Okay? However, some of these methods call the next method in their definition, and they're saying as such, because this next method could be unique to the iterator, depending on, you have to implement it. Oh, when I said depending on, it's depending on your implementation. So for example, if you had an iterator but you didn't want to iterate over all your items, or your iterator is going to have an implicit filter, so it only shows, I don't know, let's say numbers greater than 10, then you're going to show the next number that is greater than 10. Things like that. Methods that call next are called consuming adapters because calling them uses up the iterator. One example is the sum method, which takes ownership of the iterator and iterates through the item by repeatedly calling next, thus consuming the iterator. As it iterates through, it adds each item to a running total and returns the total when iteration is complete. Enlisting 13-16 has a test to illustrate a use of the sum method. So here they're going over consuming adapters, and seemingly what this means is there are some methods that they could be called on an iterator, and what they do is they consume the iterator, as in they call next repeatedly over and over and over until the iterator has no more items in it, and they do stuff with those items. An example that they gave us here is sum, which sums up all of the items within the iterator. And then we have a test down here, so let's write this out real quick. hashtag test function iterator underscore sum. Let v1 equal vect 1, 2, 3. Let v1 iter equal, oh, they explicitly wrote out total, that's what I was looking at. But this is v1 iter, same thing as last time, nothing different. And then they said let total, and they explicitly gave it a type I32 equal v1 underscore iter dot sum, which is here. And then we're asserting that the total is equal to 6, which is the summation of 1, 2, 3. See if that works. Get rid of this block thing. Cargo test. 2 tests pass. Golden. So just to reiterate what we did, we have a vector 1, 2, 3. We create an iterator, and then we called sum on that iterator, which consumed all the items within the iterator and added them together. We aren't allowed to use v1 underscore iter after the call to sum because sum takes ownership of the iterator we called it on, which seemingly makes sense. I mean, if sum takes ownership of the iterator, then at the end of the scope of sum, which we don't see here because it's written someplace else, iterator should be removed from scope, should be dropped from memory. Yeah, makes sense. Methods that produce other iterators. Other methods defined on the iterator trait, known as iterator adapters, allow you to change iterators into different kinds of iterators. You can chain multiple calls to iterator adapters to perform complex actions in a readable way. But because all iterators are lazy, you have to call one of the consuming adapters methods to get results from calls to iterator adapters. Okay. So earlier we talked about, what was it? Consuming adapters or adapter consumers. Something along those lines, where we call that, for example, sum on an iterator, and it calls next repeatedly on your iterator until it consumes everything that's in it. Now we're talking about iterator adapters, which is seemingly another iterator just attached to your iterator, as in it takes all the items from within your iterator and then does something to them, but it also just passes it on the line. They do not call next in the original iterator. That is why they're adapters, and that is why at the end you still need to call a consuming adapter on them, because these things, iterator adapters by themselves, they're just lazy. And we haven't gotten to that paragraph yet, but it looks like their example includes a map. Enlisting 13-17 shows an example of calling the iterator adapter method map, which takes a closure to call on each item to produce a new iterator. The closure here creates a new iterator in which each item from the vector has been incremented by 1. However, this code produces a warning. And this is the code. It looks like we have a vector, and then we have v1.iter, which it returns an iterator, and we're calling a map on it, which should take each item within this iterator as represented as x and do x plus 1, and that's going to be returned. However, this is the iterator itself, and it's not a consumer, and because it's not consuming the iterator, nothing's happening, because iterators are lazy, and iterator adapters, this map thing, is lazy. But let's write it out anyway. So put it underneath. Actually, no, we can probably get rid of this. Do it here. Now we can say v1 iter dot map and we're making a closure and returning x plus 1. Now when we do go cargo run, we should get a warning. And I need to semicolon. That's very true. And here's the warning. Map that must be used. We just have something that is unused, and that is this thing. So here they're illustrating the warning, which is what we have. I was looking at the top, which is here. And then the bottom, the node is here. Moving onward. The code in listing 13-17 doesn't do anything. The closure we've specified never gets called. The warning reminds us why. Iterator adapters are lazy, and we need to consume the iterator here. To fix this and consume the iterator, we'll use the collect method, which we used in chapter 12 with environment args in listing 12-1. This method consumes the iterator and collects the resulting values into a collection data type. Okay? So we already explained this first part. I mean, iterator adapters are lazy. Yeah, we understand that. But how do we go about fixing it? Well, we need a consumer. And collect, this method that we called once in chapter 12, is a consumer. And it's going to collect things into a collection data type. Okay? In listing 13-18, we collect the results of iterating over the iterator that is returning from the call to map into a vector. This vector will end up containing each item from the original vector incremented by 1. We have the +1. Everything in this individual vector is going to be incremented by 1. Right? And we're calling collect on it. So dot collect. And then we have an assert. So we just write here, assert equals. Oh, we made it into v2. I haven't written out v2 yet. Alright, so yes, here we see that collect is returning a collection data type. And if I remember correctly from chapter 12, there are many different types of collection data types. In order for the compiler to know which one we want, we have to specify it. So I think that is the reason why they said vector 2 or v2 is equal to vect, and they put that there. They explicitly said the type instead of let the compiler infer it. But we'll see what they say. And I want to say this is equal to 2, 3, 4. Everything incremented by 1. And it ran. There was no output because we didn't print anything, but it didn't error out when it hit this equal statement. So I'm assuming this is correct. Because map takes a closure, we can specify any operation we want to perform on each item. This is a great example of how closures let you customize some behavior while reusing the iteration behavior that the iterator trait provides. Yes, this is very flexible use of maps and closures, mainly closures. But I mean, what they're trying to illustrate here is that you can use this for anything you really want. If you have an iterator, you can call a map on it, and then you can do something to each and every item within the iterator. Here we just did +1, but the options are endless, boundless. And then you can call collect on it. This is a pattern that we can use frequently.